So imagine an earthquake hits a standard, fixed-base building. Because that base is just stubbornly locked to the ground, all that violent kinetic energy, it literally has nowhere else to go but straight up into the structure. You get severe interstory drift, dangerously high floor accelerations, and worst of all, catastrophic plastic hinge formation in those reinforced concrete columns. It's basically permanent structural yielding. The whole building ends up acting like this giant, rigid shock absorber, just taking the absolute full brunt of the Earth's dynamic excitation.
Which brings us to the million-dollar question structural engineers have been agonizing over for decades. How do we actually stop an earthquake from just tearing a building apart? Now, the traditional answer has always been brute force, right? Just add more steel, pour more concrete, add more mass. But what if the ultimate solution isn't building a tougher boxer, but a smarter one? What if the best way to survive the fight is to, well, just stop fighting the earthquake altogether?
Okay, let's dive right into this. Welcome to today's explainer, Surviving the Shake, the physics and data of base isolation. I'm super excited to walk you through this one. Today, we're going to break down the exact engineering mechanics that allow buildings to literally float above a seismic event. And of course, we'll be looking at the hard, empirical simulation data that proves it actually works.
Here is our roadmap for today. We're covering 5 key areas. First, the fixed base problem. Then, the mechanics of isolation, the experimental setup, decoding the data, and finally, rethinking structural demand.
Let's kick things off with Section 1, the fixed base problem.
All right, to appreciate the fix, we really need to understand the baseline physics of a standard, rigid structure first. In a traditional fixed-base system, the superstructure is rigidly attached to its foundation, and from a physics standpoint, that creates a massive vulnerability. See, the inertia forces that develop during a quake are directly proportional to 2 things: the building's mass and the ground acceleration. As ground acceleration ramps up, those lateral forces ripping through the building ramp up right along with it. To prevent collapse, engineers get backed into a corner. They have to continuously increase structural capacity and lateral stiffness. You're basically turning the building into a massive, rigid target.
Which brings us to Section 2, mechanics of base isolation. Let's look at the physical hardware that completely rewrites this whole destructive dynamic. What we have here is a spherical sliding isolation bearing, strategically positioned right between the building foundation and the column base. Whether engineers go with a sliding friction pendulum system like this, or maybe laminated elastomeric rubber bearings, the mechanical goal is exactly the same. We want to introduce a highly flexible, decoupled layer right at the foundation. We are structurally separating the building from the very ground it sits on. And this brilliantly illustrates the resulting shift in structural behavior. In a fixed building, you get these huge induced forces causing massive lateral displacement in the superstructure itself. I mean, that is exactly what causes your concrete to crack and fail. But when you look at a base-isolated structure, it's a completely different story. The internal structural forces are incredibly small. The building itself stays relatively stiff and still, while massive lateral movement is accommodated entirely within the isolators down below. The earth shakes, the foundation moves, but the superstructure, it's just safely gliding above the whole shebang. Now, to truly grasp the engineering magic happening here, we have to talk about the fundamental time period. Think of this as the natural rhythm, the exact amount of time it takes for a building to complete one full cycle of side-to-side movement. Earthquakes pack almost all their destructive energy into highly specific, very rapid frequencies. By introducing that flexible isolation layer at the base, we are drastically increasing the building's fundamental time period. We are essentially slowing down its natural sway and shifting it completely out of the earthquake's high-energy danger zone. Moving on to Section 3. It's one thing to understand the theory, but let's actually look at the simulation methodology researchers used to empirically prove this concept. Structural engineers went in and rigorously modeled 2 identical, 6-story reinforced concrete residential buildings to compare their journeys through a simulated seismic event. They built a digital twin scenario in ETABS using finite element modeling. One building is rigidly fixed to the ground, and its exact replica features rubber base isolators under every single column. To actually test these models, the researchers ran a time history analysis. Now, if you're a structural design student, you already know this is the absolute gold standard. It's a step-by-step numerical evaluation that analyzes the structure's dynamic, hysteretic response. Basically, that means looking at how it absorbs and dissipates energy through cyclic loading, and it does this frame by frame over time during the dynamic excitation.
It lets us observe the precise second-by-second internal stresses and deformations of both digital twins as the simulated earthquake just rolls right through them.
All right, Section 4, decoding the data. Let's see what happened.
Now, what's really interesting here is looking at the hard numerical results. This is the dramatic climax of our comparative analysis. The simulation revealed a massive mathematical shift in the isolated building's natural rhythm. The fixed base building clocked a fundamental time period of 0.47 seconds, but the base isolated structure? It lengthened its period to 0.604 seconds. Guys, that is a whopping 28% increase in its fundamental time period. So what does this all mean? The absolutely crucial point is this. Lengthening the period equals escaping the destructive frequency. By shifting that natural period by 28%, this mathematical change actually acts as a physical filter. It fundamentally blocks those rapid high-energy ground motions of the earthquake from ever violently transmitting up into the superstructure.
Next up, structural response reductions.
How did that 28% shift actually affect the physical stress on the concrete and steel? Well, prepare yourselves for a staggering plunge in structural distress metrics. The simulation revealed a massive 69% reduction in base shear. Base shear is the maximum expected lateral force that'll rip through the base of a structure due to seismic activity. So by introducing that flexible isolator, nearly 70% of those ripping forces were totally neutralized before they even had a chance to touch the structural columns. That's incredible.
And to punch the impact even further, the researchers recorded a 75% decrease in top-story acceleration. In fixed buildings, you know the top floors often whip violently back and forth, acting almost like a reverse pendulum. That's what causes severe concrete plasticity and, ultimately, collapse. A 75% reduction means that whipping effect is practically eliminated. The top floor of the isolated building stays remarkably calm compared to its fixed-base twin. Finally, let's wrap up with Section 5, rethinking structural demand.
It's time to bring all this simulation data back down to earth by examining the overarching engineering philosophy it proves. The research paper summarizes this whole paradigm shift with one brilliant quote. Base isolation systems attempt to reduce the demand rather than increase the capacity. This right here is the ultimate lesson in modern structural engineering. We obviously can't control an earthquake's power, but through highly intelligent design, we can profoundly modify the demand placed on our architecture. Let's contrast these two paradigms side by side to really cement your main takeaway. On one hand, we have increasing capacity, adding thicker concrete, heavier mass, and immense stiffness to just stubbornly fight seismic forces head-on. On the other hand, we have reducing demand, using base isolation to gracefully decouple the structure, fundamentally bypassing the physics of the earthquake and avoiding absorbing those forces altogether. One approach relies entirely on brute force, the other relies on physics.
So I'll leave you with this final, provocative thought. As urbanization pushes our cities deeper and deeper into high-risk seismic zones, is it time we finally stop building structures to fight earthquakes and start building them to float above them? Let that visual metaphor sink in as you approach your next design challenge. Thank you so much for joining me for this explainer. I really hope it sparked a new level of curiosity for your structural engineering journey. Keep learning, stay curious, and I'll see you next time.